Welcome, Fernando, on stage. Fernando from Race 3D. Maybe introduce shortly yourself, and then we are really looking forward to metal 3D printing.
Okay, thank you, Leo. Yes, so this is Fernando from Race 3D European office. We have an office in the Netherlands, from where we handle all the European business. First of all, I would say I'm from Spain, so forgive my strong South European accent. But considering the time of the day, I should be sleeping siesta now, but yet I'm here. So, okay, let's talk a little bit about metal printing today. So, metal is kind of like this scary thing that people is afraid to touch or to address, because it's a not understandable technology. It's not easy to get to understand metal. We only have 15 minutes, so we are still inside my mark. But this is what my ex used to say, so should be enough to explain everything about metal in a brief. First of all, where does metal stands out, or what is the strength of metal printing? Well, for start with, strong mechanical or superior chemical properties, chemical resistant properties. There are some plastics or polyamides that they can get close to, but they are not there yet in both mechanical or chemical resistance, so metal is still premium there. And you have quite a lot of design freedom in the technology that we are going to touch today in comparison with other metal printing technologies. We can make lightweight parts yet almost as or similar mechanical properties as the full thick printed parts, thanks to lattice structure in metal printing you can do. You have, in this kind of technology, in additive FDM, for example, for metal, you have more material efficiency. You don't have so much waste as a CNC. In CNC, you have a block, which you need to kind of sculpt, and then you have a lot of leftover material. So material means cost. You have, of course, the possibility to do direct metal prototyping. So we try to do prototyping on plastic, and then try to see if it fits or if it can support or withstand the properties. But here we can directly do metal prototyping. And the last but not least is you have in-house production. So you can shorten the times if you want to print metal, not only prototyping, but also production. So you shorten the times where you depend on external labs or external services. Okay, so with a brief introduction about metal, there are a bit more, but basically the three major technologies to print metal. We have powder bed fusion. So here, this is also known as SLM. You can have a bed full of powder and a laser, which is sintering together, and then you have the part. You have some advantages, some disadvantages, but the biggest disadvantage is the powder metal is very difficult to deal with. It's explosive. It has a lot of side effects on the laboratory itself, on humans. So it's kind of a tricky and difficult and dangerous material to deal with. Then we have binder jetting, which is similar idea, but instead of using the laser to bind together the metal, you use a binder. So a binder, which is layer by layer, is binding the metal powder and is creating these 3D shapes. Again, the same issues that we are talking about SLM. You are dealing with powder metal, which is somewhat risky. It's also difficult to handle, extremely messy, etc. So that's two of the technologies printing with metal. And then we have metal FFF, which is you can print parts as you print plastic parts, and then you get them into metal. How does it happen? We will see today. We have a kind of a quick explanation about the process, but that's a brief introduction about the three current technologies that you're going to print in metal. Now, what are the challenges or the difficulties of adopting metal into our own lab? It is quite of a trip to learn or to teach the workforce to handle metal printing. Alas, plastic printing can be learned in a few minutes. Metal printing is kind of acquired knowledge. You need to require some training before printing, processing, post-processing. It is quite a trip. So it's one of the barriers. Sometimes in some metal technologies, for example, the 1 kilowatt laser metal printing, you need to, the part is built into a metal plate, so you need to dismantle, so you need to cut the part from the plate, and that also requires external ancillary equipment, which is complicated, difficult, expensive as well. In same go for the support materials. Some of those printing, the support materials need to be a kind of a cut with a special machinery, so it's not easy to remove. You cannot remove the hands like in the plastic parts. Also, if you swap between materials, talking about the powder metal, for example, it's extremely easy to get contamination. You get not only several risks involved, but also affect the final part, the mechanical properties. And that means that the switching between materials requires for a few hours of deep cleaning before when you change from one material to another. And yes, the loose metal, the powder, as I mentioned earlier, is dangerous and is risky and is a hazard to add into the equation of difficulties of printing with metal. And the last, which is printing metal, is not everywhere, but one of the challenges is it's very expensive. And price is one of the things that is forbidding many partners to jump into metal. Not only the barrier of knowledge, but also the cost of ownership is quite high. Okay, so, but what if, only if, we could have a machine that can have easy to change materials, loading and unloading, as we do on FDM, which is basically swapping a spool. You change material by swapping a spool. That would be amazing. What if you have safer and easier handling of the material? You don't need to deal with the dust, with the powder, and the whole process is as clean as FDM printing, plastic FDM printing. And what if you can easily remove the supports with your hand? You don't need to have special equipment, you don't need to have special machinery or a special process to remove the part from the support. And what if we could make it affordable? Okay, so I introduce you the metal fuse system from Race3D, which is the system itself is including, well, it's made of 3 independent devices. So we have the printer in one side, which is a strongly modified FDM printer, but at the end of the day, it's a FDM printer nonetheless. We have the debinding furnace to convert, so with the FDM printer, we get the green part, then the debinder through a chemical process, it will remove one part of the binder, and the last step, we go through the furnace, which is the brown part we put into the furnace, and then we get the final metal part. This is what we are looking for. So we have 2 post-processing possibilities. So yeah, this is the printing journey. So we go from the typical, the first part is pure, 100% pure FDM SOP. So you design the part, you prepare the part, you go into the software. We have the software. The software will calculate the shrinkage rates for the parts when you print versus when you get the final part. So it's as close as possible to your CAD/CAM model. And Then once you have the part, you go, which is the green part, you go to the debinder, which is, like I mentioned, through a chemical process, it will remove part of the binder. And once it's done, then you go through the sinter part, where is the final stage through an oven. It will basically heat up and burn out the rest of the binder. And then you have the full metal part. We can see here, in the sample case, we have another case that we will rotate so everybody can see. We have, this is the part as coming out from the FDM printer. So you can see, of course, it's slightly bigger than the final part. So the same applies to this part or this part. So they are all, the green part this is as it come out from the printer. This is after the chemical process and the furnace. And this is the final part, polished. The polishing, electropolishing, we don't have a device for this, but this is available, plenty of choices and options on the market. So green part, final part through the polishing process. I don't know if camera catch that. Yeah, good. Yeah, that's the green part has come out of the printer. That's after the whole process, the middle one. Yeah, that's after the whole process. And that's the same part with post-process. Okay. The good thing of having separated systems is flexible in regards of cost of ownership or cost of running. So in example, to own the whole system, you have full process control. The whole printing process is under your control. It's faster production because you hold the whole process. On the contrary, the cost of ownership is a little bit higher. So the possibility is you only own the FDM printer, the Forge1, which is, again, has the price of a powerful and very advanced FDM printer, but still fairly affordable. And you can rely on external services which are all over Europe, including Germany, that they will post-process the parts for you. So that's also a possibility. So you can have the part, you can create your own parts, and then you just need to send to external services for the final steps on the post-processing. We work in terms of materials, obviously, with some partnership with Forge1. They have, well, at the moment, 3 different materials. We work with stainless steel, 2 different versions, and the support materials for the metal parts. One of the things that we also need to be transparent or clear is metal printing, if you own the whole system, you need to try to optimize, because it's a high investment, you need to optimize the output. And to optimize the output, you need to optimize the machine and the ancillary. So that's one of the limitations. I'm going to speak about that in a bit. You also have the benefits, but also the disadvantages of FDM printer, which means you rely on the extruder nozzle diameter as your resolution. We have few options, so in this regard, it's not much of an issue. And currently, like I mentioned, we only have 2 possible printing materials, which are stainless steel in 2 different compounds. One offers more corrosion or chemical resistance, the other one more mechanical strength, so depend on the final usage of the part. But for the moment, we have only 2 materials available. What will be the best possible, or the most optimal scenario? So you have 1 debinder and 1 sinter machine. The post-processing machines can handle the print output of 8 Forge1 FDM machines. So that will be the most optimal scenario. And that affects a lot, sensitively a lot into the final part of the cost. We will see in a bit. We have 0.2 nozzles, so you are allowed to print very detailed and fine parts. You can see the scale here is really, really tiny for metal printing. And again, this is the final part. All the details and the accuracy. Okay, but let's talk about cost, which is important. Because at the end of the day, it's an investment, you need to get a return of investment. So we have three parts. So part A, part B, or part C. So an example, the part A, which is the most detailed one. If we want to use C&C service, by these prices we go by isometry, but there are other services available, so prices are fairly similar. So you can get this part for 820 euro. If we use powder bed fusion, it's a little bit cheaper, almost half, so 422 euro. But if we do our own print part in-house with our own system that we own ourselves, and we even add into the cost the depreciation of the machinery, by printing this part, you have a total part of 8 euro for the part, the gas, the power, the depreciation. So you have a part for less than 100 euro. And the part B is also similar, so 1,400 euros. It's a little bit bigger. So 500 euro if you do powder bed fusion, and if you do in-house with our system, the part of the cost is 126 euro. Again, include all the cost of material, depreciation of the machinery, power consumption, and gas consumption. Gas, by the way, which we need to use inert gas, so we use argon and nitrogen, which both are fairly cheap. And the last part, the fee. And if you print all of them, then you even get lower. So, but that's per part. So how would you optimize if you have production about parts? How would you optimize this scenario? Is where we jump into I mentioned earlier, a cost calculation relying on number of parts, or what is your output, and what is your funnel. Because, in example, if you print with one printer, the same part you print 28 times, so the cost per part is 37 euros. But if you hold 10 Forge1, including only one sinter, one furnace, then the cost per part is 14 euros. So you drastically kill most of the cost if you increase your output. And it can go all the way up to, if you print 1,400 parts, the cost per part is, again, extremely low. So the more printers you have to fit the ancillary equipment, the post-processing machines, the most efficient you get cost per part. And that's the key that we are looking after. This is new system for us. We work only for 1 year and a little bit in the market. We already have some successful case studies. So we just mentioned some quick examples. So we have Mipatec in Brazil. So they use metal for the production. We have in Europe, not particularly in mainland Europe, but in Iceland. We have an installation in Reykjavik, where they use in a shipyard for making parts for spare parts for boats. This is pretty interesting because they have a serious bottleneck in regards of supply for parts in Iceland because of the distance. So the shipping yards are always in need or in demand for parts. So metal printing in this regard is extremely useful for them, and it's basically a lifesaver. We have another company also in Brazil that they also have our metal fuse. We don't mention names. Sometimes they don't want to disclose, or they don't want us to share the system, because for them it's like giving them competitor advantage versus competitor, and they don't want to disclose. The same goes with China. We have another client in China. They already have a metal fuse whole system installed in-house. And we are even printing benchmark for clients, and we are already getting impressive feedback about, it's very often that you get metal parts with cracks, and we are making benchmarking and samples for clients, and they don't have any cracks, so they are happily surprised about the final quality of our metal parts. So yeah, that was it. Any question regarding our system? If we have time, I don't know.
Do the parts shrink in a linear fashion?
The parts shrink in a non-linear fashion, but the software calculates, depending on the mass that you have, it will calculate the shrink ratio. So you don't really need to worry much about the shrinkage because the software will pre-calculate for you. If you print one part and it's really, really off, you can still make manual adjustments on the profile, on the shrinkage ratio. But typically, most of the time it's pre-calculated and it's adjusted automatically.
So is it shrinking more in the Z-axis, for example?
Yeah, in this case.
Okay.
And the shrinkage is relative to the proportion of the binder in the material itself.
So the more mass, the more it will shrink. So the software should be able to compensate. But still, we are talking about FDM tolerances here. So not injection molding tolerances, for example.
Will you offer a Sinter service for that? That you can design in-house and then send you the pieces and you will do it for a number of companies because that makes sense in your case.
Yes, we have in-house system. So we do the binder or the Sinter process for other companies. We do already. So we have the system running, currently running. Clients that they own the FDM machines, but they don't own a Sinter or a Debinder machinery. We do.
And it's your in-house machine.
It's our in-house machines.
Yeah.
So you can prototype with this environment.
Yes, it's everything in-house. We don't need to rely on third party or so any kind of IP. So it's respected. In some cases, some big clients, we already signed NDA in advance. So we already have that secured. But yes, we have secure in-house post-processing solutions. That's it then? Oh.
What's the density you can achieve compared to like bulk material?
Density about?
Like 100% compared to like a poured piece of stainless steel.
Same.
Poured is the same. It's dasselbe wie ein Gussteil.
Or like a machine, say we have a block of 316.
That's a little denser, but that's with investment casting the same.
Yeah, the binder, once after post-processing, the binder is out in 99.8, I think. Something like that. It's extremely, the binder should be totally out of the part, finally. So we are not maybe 100%, but 99.8 or 99.9 even. Yeah. Okay. So that's it about metal printing. Thank you. Thank you. Thank you, Leo.
Fernando, really great. I learned a lot today about metal FFF. I think if I saw your faces, you were all quite amazed by the capabilities of metal FFF. And yeah, if you have some questions, just ask Fernando or me afterwards. And yeah, are there any questions from chat? Not so far, so that's good.